Video 3. In the last video, we looked at a couple of different sequences and took their limits. The first one, the limit didn't exist. The difficulty was that the terms ping-pong between negative, positive, negative. The second one, we were able to argue that by following a curve, which we know tends to 0, we could just pick off various points corresponding with counting numbers to get that the limit of the sequence is 0. Let's talk about limits of sequences. So, if we take the limit of a sequence and we get L, and L is a real number, therefore it's a finite number, then we say that the sequence converges. If L, for example, is infinity, we would say that the sequence diverges. If we don't get a real number L, the sequence diverges. Here are some examples. Let's take a sequence. First one is, hey, it's going to alternate. We saw that before, but the top alternating is always producing a plus or minus 1, whereas the denominator is the index, and that index is going to get arbitrarily large. The top, therefore, has no chance of overcoming the bottom. In other words, this sequence will converge. It will converge to 0 as n goes to infinity. Come back and make a statement that sequence converges. Do the next one. In contrast, we have a constant. Take away 4 times the index, and again the index wants to get arbitrarily large. Therefore, this guy is going to send the sequence to negative infinity as the index goes out to positive infinity. Negative infinity is not a real number. We therefore say that this sequence diverges. Good. Another one. Third example, where we do a little bit of algebra. And if we start with this as the nth term, so you have a polynomial degree 4 on top, a polynomial degree 4 on the bottom. You look at the bottom, and then you take each term and divide it by the variable raised to the degree of the bottom. Doing so, n would go to 1, 6n cubed would go to 6 over n, and so forth. This term will go to 0, this term will go to 0, this term will go to 0 as n goes to infinity, leaving you with just 1 and negative 5 in the bottom, or negative 1/5. Negative 1/5 is a real number, so this an converges. Good. That's a limit of a sequence, and you want to know the words converge. You get a finite limit, or diverge, all other situations. Okay. So let's talk about the limit of a sequence defined by a function. Let's take that the sequence has nth term given by the function given by some function at a counting number. Then if the function, as the input x's go out to infinity, limits to a finite number L, then that's going to imply that the sequence as well has the same behavior. We used this in the previous video where we thought about a decaying exponential, and along that decaying exponential we just picked at the counting number inputs our terms of the sequence, and the terms of the sequence followed the function, and the function had a particular behavior, letting us conclude that the sequence will have the exact same behavior. So take a look from the previous slide. If we do 3 minus 4n, that's the same thing as f of n. If we set f of x to 3 minus 4x, we can look at the graph of f of x and then pick for n equal 1, for n equal 2, points on the graph, and we can see that those points would tend towards negative infinity. In other words, this guy diverges. Try another one. Let's say that we consider cosine of n pi over 2. So we can identify a sub n as f of n if we set f to cosine of pi over 2 times x. So draw cosine. And a sub n is going to be the points with outputs 0, negative 1, 0, positive 1, 0, negative 1, back to 0, positive 1. So those output values are the values, the terms of the sequence, and they're not converging to a value. So this an diverges. Good. This an defined as sine of 1 over n divided by 1 over n. I'll invite you to create a Desmos graph to plot these points. Try another one. A sub n, let it be ln of n. Graph ln of x. Consider when n is equal to 1, n is equal to 2, n is equal to 3, and so forth. Well, you just need to remember that the behavior of ln is that it tends towards infinity. Therefore, an will tend towards infinity. So this guy diverges. Sweet. So here we're taking advantage of finding the limit of a sequence by considering the nth term defined by a function, and then just thinking about the function. Okay. Limit laws. So way back in first semester calculus, you would have written down these exact limit laws, but for functions. Let's take a look. We have some assumptions. Suppose that we have one sequence and a second sequence, and they converge respectively to a and b. So the a-ends converge to capital A, finite number, and the b-ends converge to finite number, capital B. Next, we'll use a constant c as a real number and consider 5 different laws. For the first law, we're simply stating that the limit of a constant is the constant. That should be very familiar. The only thing that's new here is that we're only picking counting number inputs. We have a sequence, a sub n. If we multiply it by a constant, that constant can be brought to the front, and then we can evaluate the limit of the sequence. By assumption, we're saying that, assuming that a sub n converges to a. So we get c times a. Third limit law is a sum or difference. Basically, we can distribute the operation of taking a limit to each sequence, and then find their limits individually and add or subtract their limits. So third limit law was the operations of addition or subtraction. The fourth limit law is swap out that operation with multiplication, and you have basically the same statement. On the fifth limit law, change the operation of multiplication to the operation of division. And same idea, you can distribute this limit to the numerator and to the denominator to get a quotient of limits. And you want to form up the quotient of their limits, noting that we cannot divide by 0, and we cannot divide by 0 in the original quotient either. So the limit can't be 0, neither can any of the terms in the denominator. Good. So these are limit laws. Should be very familiar. Okay. One last idea. Squeeze theorem. We've seen the squeeze theorem in a first semester calculus course. Same notion, except now we're stating it in terms of sequences. 1, 2, 3 different sequences. Find a value n such that for all indices past that value, the following inequality holds. Then look on the outside terms and assume that those outside terms both tend towards capital L. Then that's going to force the inside guy to also tend towards capital L. Good. That's the squeeze theorem. Do an easy example. And the second one, leave as a challenge. All right. So sine of n is just the sine function. And when you think of the sine wave, you know that it's trapped between +1 and -1. So you use that information. That an, at least its numerator, is trapped between +1 and -1. And then look at the denominator of an and just let it be. Then you can clearly see that as n goes to infinity, the left sequence goes to 0, but also the right sequence goes to 0 as the index goes to infinity. Therefore, the limit of an will also be that capital L 0. And why is this? What have we done? We've applied the squeeze theorem. Nice. And I'll leave this one as a challenge. And I'll remind you that the sine wave at the origin has tangent y = x. Excellent.